Am I audible? So
Yes, ma'am.
this is about use of UV visible spectrophotometer for analysis of biomolecules. We know that the light is absorbed by a sample analyte. It may be absorbed, it may be reflected, it may be transmitted. So based on these properties, we can characterize the molecule, its concentration, then its purity, it's said to certain degree it's a variation with respect to structural composition, that is if any metal is binding with it, if ligand and protein they complex, they form a complex, or enzyme binds to a substrate, so on and so forth. So let's talk about the design of the instrument. When we talk about UV visible spectrophotometer, the monochromators are the important component, right? So when I say monochromator, what comes to your mind? This is the design of the instrument. The leftmost, what you see, a block design in blue, is nothing but the tabletop UV visible spectrophotometer. And now, if from this, what I see is the monitor here. Here are some buttons which here are used to provide the command to the instrument to select the light source, whether to go for white light or tungsten light, or you have to go for UV light, whether you are going to go for absorbance measurement or transmitter measurement or concentration measurement, etc. What is the temperature of working? All these details are here. And this is the flap. If you open it, you will see the sockets for holding the cuvettes. So once you place the cuvette, you have to cover this lid again, this blue color shuttle, and then you can go for starting the estimation. What is the components or design of the instrument? From outside it looks like this block, but inside, if you see, it is the light source, then the entrance slit from which the light will be allowed to enter, but a small quanta of light is allowed to enter. The slit dimensions in terms of the pore of the slit, or the gap through which the light passes, that is going to play a crucial role. You have two slits, one is for entrance slit and another is exit slit. So the gap distance, or the slit distance, is very crucial in spectrophotometric analysis. So here light passes through the entrance slit, it enters the region which is referred to as monochromator region. As you can see here, you are seeing the prism, right? We are going to talk about all of them. And from the prism, the white light is going to get uh, distributed, or uh, you can say fragmented into its component units, that is Vibgyor. Out of that, the desired wavelength can be selected by giving an instruction here, which wavelength you want to work with, and then that component only will be selected. As you here, you are seeing only the green portion of light, and that to a specific wavelength you can select, which will pass to the sample, and then the absorbed light or the transmitted light, or directly the concentration, whatever command you have given to the instrument, that will be analyzed by the detector and it will be displayed. Now, when I say a monochromator, that is very crucial component in the spectrophotometer. Otherwise, the very simple thing that you have as a color emitter in the lab, which has got filters that selects a wave band, right? 430 to 470 nanometers at a stage, maybe. So you have different types of filters, but it is a wave band. You don't select a single wavelength. Here you have a monochromator, which is going to monochroma, is going to select a single color, but not it is not limited to color alone, but it is limited to the specific wavelength that you can choose: 260, 265, 280, whatever it may be, in the UV region. And in the visible region also it can select, because you have UV visible spectrophotometer. If you are working with UV spectrophotometer, you will choose the UV lamp. If you are working in the visible region for analysis, then you are going to choose the light source, which is visible light source. Now here I want to show you how this monochromator is going to work. Monochromator is nothing but you can say assembly of mirror optical components, which will include mirrors, prisms, and diffraction gratings. So what are they? How do they work? That we have to learn in details. So when I say the light source, which is going to allow the light to fall onto the mirror. So here the entrance slit is there, the light passes through it and it falls on the collimating lens, that the one which is going to collect the light, right? From that it will be projected to the gratings here, as you are seeing in the diagram. Gratings, what are gratings? We are coming to it in, to talk about in details, but just now you can remember it is high glossy thin sheet of alumina, and as you can see it, its surface on one side is smooth and another side it is eroded or it's rough, but that roughness is so fine and tuned, that is it is not even 1 micrometer size, that is you can say engraved onto it, right? So the rough surface is created by marking on the very fine and polished surface. You are going to have like embossing, right? You just emboss a particular design by beating the metal surface so that a design gets developed. Here it is carved, you can say, or marked, you can say, are the fine lines which are 1 micron diameter or even less. Distance between the two is there, so whatever light falls onto it, these gratings are going to work like the prism and is going to split the light into component wavelengths, right? That is you are seeing. So that those light which is broken down into its component wavelengths is collected by focusing mirror, that is going to pass through, will be collected by another optical system which is going to condense focus that light, and the collected light will be passing through the exit slit, and from the exit slit it will go to the sample. Now here we have shown only one, that is the diffraction grating, but you can have a design where the prism and gratings both are assembled, so you get even better focusing and selection of a particular wavelength. So this is the schematic diagram that shows how is the input, right? What is the input? That is the light, di, right? As you are seeing here, it is entering from this point, right? F is the focal point, and then here you are seeing the signs which are known to you. This is d0, that is the output slit, right? And here are the spherical mirrors, right? So this is the assembly in short when we talk about a monochromator. So optical device, in one word to say, what is a monochromator? Optical device, what for? To obtain a narrow band wavelength or a single wavelength that you can adjust. So that will be transmitting to your sample. So incoming light which is entering through the entrance slit, which is called as DI, and then it is collected by spherical mirrors of focal length f placed at a distance f from each other and from the entrance slit, and after mirror a flat wavefront is formed and directed to the gratings. So here are the gratings, they will collect, or this is the grating, the surface of the grating, and the collected light is going to be diffracted, and that light is going to be thrown on the mirror number 2, the spherical mirror number 2. This is going to collect that light and is going to direct it to the collecting mirror. So that is how the monochromator is going to work, right? So when I say monochromator, it is going to consist of absorption filters, optical devices, interference filters, cutoff filters, so on and so forth, right? It is going to have mirror and it is going to have gratings. Now when I say the gratings, as I told you earlier, these are the thin alumina sheets, highly polished sheets, and there are grooves on it. So there are hundreds and thousands of grooves within 1 millimeter area. So higher the grooves, better frequency selection you can get, better optical resolution you will get, right? So lower groove frequency provides usable wavelength range which is higher, but resolution will be bad. So what do you want to have? High groove frequency, which is going to give you a good quality resolution and better selection of a desired wavelength, right? So most commonly monochromators are used for the process so that lambda max, that is absorbance maximum, which is the characteristic property of any analyte molecule, can be provided, and you can detect the purity of the molecule, the concentration of the molecule, structural details can be conferred, etc. So this is about the monochromator, right? So this is the short note you can say about monochromators. So the simplest of wavelength selector is a monochromator, which is optical filter that you have used, but the advanced one is the monochromator that you are using here. So what is going to do? The simplest of monochromator consists of rotable diffraction gratings or a prism or together, right? And number of mirrors which are going to direct the beam, light beam from which is entering from the entrance slit, it will be directed to the exit slit, but through these channels. So there is prism, there are diffraction gratings, there are collating mirrors, there are then spherical mirrors, so on and so forth. So spectral bandwidth of the light can be produced, and the monochromator optics is going to help in that. So and when you talk about the wavelength of the light, that is lambda, is better considered as having a distribution of wavelengths. So the weights of the distribution about lambda being given by SBW. What is SBW? Spectral bandwidth. So a single monochromator may achieve spectral bandwidth of 5 to 10 nanometers. Whereas accurate spectroscopy, when you require 1 nanometer difference, that is 260, 261, 262, 260 nanometer, like that, a single wavelength difference, then you are going to have monochromators in series. So prisms and diffraction gratings and sets of mirrors all are arranged in series so that a good precision you can achieve, and the SBW, that is spectral bandwidth, as less as 1 nanometer you can have, and it is going to be very appropriate. Now, when you talk about sample analysis, as you use the colorimeter in a similar fashion, it is used here. You are going to have a blank, reagent blank, water blank, or the solvent blank, and the analyte. The analyte is kept in the sample holder. You change the lambda value, and you find where it is giving you highest absorbance. The lambda, or the wavelength which gives you highest absorbance for a given analyte, is referred to as lambda max. And at that particular lambda, at that particular wavelength, you are going to do all the estimates or analysis of the sample where this particular molecule is present. So presence of the desired molecule in a given sample, what is its quantity or concentration, what is its pure degree of purity, all these things can be analyzed. So lambda max is the concept where a particular analyte gives maximum absorbance, that wavelength you are going to choose. So a wavelength where analyte gives maximum absorbance is lambda max. All right. So now when you talk about keeping a sample, you need a sample holder, that is cuvette. As we talked earlier in a previous lecture, quartz cuvettes are there for UV region samples to be analyzed in the UV region. Glass cuvettes are useful for visible region, and plastic cuvettes are also available. Now, why we need different types of cuvettes? For example, majority of plastic cuvettes are inappropriate for UV absorption studies because plastic also will absorb UV light. When you talk about glass, glass can act as a filter, and often it will absorb the majority of UV light in the range of 100 to 280 nanometers. And another is UVB rays. UVA, UVB, UVC are the types of components of UV rays. So 280 to 315 nanometer, but allow only UVA rays 315 to 400 nanometers to pass through. So glass also hinders transmission of the entire range of UV. So here, quartz sample holders are required for UV examination because quartz is a transparent to the majority of UV light. So depending upon the type of spectrophotometer or the analyte that you are using, you are going to have the type of uh, um, uh, sample holder, right? There is mm, examples of absorption spectra that we have to talk about, right? Now we have talked about monochromators, by now we have talked about sample analysis. Now let's talk about the detectors in details. At the end of the topic we will discuss, but right now let's go for the applications or use of UV visible spectrophotometry in analyzing biomolecules. So here, as you can see, it is the range, that is the wavelength on x-axis that is placed, and on y-axis you have the absorbance values. So as you can see that the absorbance, say about 0.25 is seen at the starting point, that is 250 nanometers, which drops again near 350, and there is again a sudden rise around 400 nanometers, and then again a drop, and there is no absorbance at 700. So this schematic representation shows that the lambda max of the analyte under study is around 400 nanometers. So that is how you can find the lambda max of a given analyte, and then rest of the analysis can be done at that particular wavelength. So wavelength, when you are talking about for protein, for example, it is 230 nanometer, which is useful uh, in analyzing the change in the protein shape on binding with the any ligand. It can be substrate, metal, etc., etc. Then at 260 nanometers, DNA and RNA both they absorb. So you can use it for measuring the concentration of DNA, check the purity of DNA, and even the structural forms of DNA can be analyzed using UV visible spectrophotometry. We will come to that. Then at 280 nanometers, again proteins they absorb mostly which contain tryptophan and tyrosine. So these are the specific wavelengths at which you can set your spectrophotometer when you are analyzing biomolecule like protein, DNA, RNA. So for protein, the best is 280 when you are talking about protein having tryptophan and tyrosine. 260 is good for nucleic acid. That is how. Now, when as I say, these concentration can be detected based on the absorbance values. More the absorbance, that indicates more is the concentration. So as you go on increasing the concentration of analyte, the absorbance value for the analyte will go on increasing, and you can get the proportionate increase in the absorbance values. So for the unknown sample with the analyte, you can have a standard graph initially prepared with the known concentrations versus absorbance. That graph is prepared, and the absorbance of your sample analyte is measured, and you are going to use the standard graph for finding out the relative concentration of your analyte under study. Now, second thing I said, you can use DNA RNA estimations, not only concentration, not only purity, but yes, to know the structural variation. That is how whether the given DNA is in the form of double strand, or has it molten, or is a single stranded molecule. Because as long as DNA is double stranded, the absorbance is say X, say 2.25 for a given concentration of DNA. But if you give a higher at a higher temperature, if you heat your DNA sample, then what is going to happen? DNA is going to melt. That is, the hydrogen bonds are going to melt, and strands will start separating. As the strands separate, the same concentration of DNA is going to give you higher absorbance. Earlier, what we said, concentration and absorbance are directly related. So absorbance is proportional to concentration. So more the absorbance, more is the concentration. But here what I'm saying, concentration is maintained same, but you have given heat to the DNA, so it starts melting, and double stranded DNA is converted to two strands, that is single stranded two threads are formed. So here absorbance will go on changing as DNA goes in the transition phase from double stranded to single stranded. So in between, what will be there? Some of the bonds are broken, some are still persisting. So in that phase, the absorbance will be more than the earlier, and as the two strands they separate, it will be even higher. So as you can see here in the diagram, as you go on increasing the temperature, so melting of the DNA will increase, and that will show proportionate increase in the absorbance value. Initially till 55 57 degrees Celsius there is no melting, and there is no change in the absorbance values. But as you go above that, melting of the DNA, breaking of the hydrogen bonds is facilitated due to the energy uptake, and DNA strands start melting. So as the more and more hydrogen bonds break, more and more part of the double stranded DNA separates into two single strands, you will get increase in the value of absorbance value. This will happen till both the strands are totally separated as single strands. So this is what we have used um, to analyze whether the given DNA is in the double stranded form, whether it is in the single stranded form. I mean, is there any transition? Is there any change that you are observing? And yes, this is a very much fundamental experiment in finding out the melting temperature of DNA, TM value, which has got lot many applications, not only with respect to ATGC composition of the DNA, but it will reflect upon the the percent of GC to AT ratio. Also, it will reflect upon the number of, or the size. Bigger the size of the DNA, more it will take to melt. That is another thing. Complexity of the DNA, that is another thing. And all this data has applications in classification and systematics of bacteria or organisms. Right. So TM value. So you can use UV visible spectrophotometer, and with the help of absorbance of given DNA solution, you can find out all these things: concentration, purity, then GC value. You can find melting temperature, so on and so forth. So these are the applications of UV visible spectroscopy. You can check for the purity of DNA. That means you are going to go for the ratio of two things. That is, you are going to take the DNA solution, you are going to take the absorbance at 260 nanometers, then you are going to change the wavelength, you are going to note the absorbance as 280, and then you are going to find out the ratio of absorbance at 260 upon ratio of absorbance at 280. So 260 by 280, right? This ratio you are going to find, and if that ratio is 1.8, then you say yes, it is your DNA. If it is little higher than 1.8, you can say probably, I mean higher than 1.8 is 1.9 or 2 or little more than that. You can say there is contaminating RNA present. And if the value is less than 1.8, the ratio of absorbance at 260 upon absorbance of 280 of a DNA preparation, then you can say the ratio less than 1.8 indicates contamination with proteins. So purity of DNA you can check this way. Structural changes in the DNA can be monitored. So these are the few examples when we talk about use of spectrophotometer in study of nucleic acids. Now here it is, when we are talking about purity, you can take this slide as a description for whatever we have discussed till now. Now the graph, if you see here, 240, 250, 260 till 340 nanometers. So you have not taken a single wavelength, but you are scanning over the range, and you are trying to find out the absorbance at specific wavelengths. So here you see first peak, which is around 230 nanometers, another peak which is at around 260 nanometers, then there is another peak which is at 280 nanometers. So 260, 280, 230, all these things are going to indicate variations. So 230 and 280 indicate presence of protein. At 280 you have proteins with tyrosine and tryptophan specifically. So 230 indicates peak of protein, 280 indicates peak of protein with DNA, and here it is 260, that is the range where DNA absorbs. So here this graphical presentation also can be used as a summary of how spectrophotometer can be used for analysis of nucleic acids and proteins. Now here that is another concept I just want to introduce, not going to go into details, nanodrop. So here you are going to work with a sample which is as less as 1 nanogram per microliter as such. And these concentrations can be calculated using the spectrophotometric methods, right? And what is the equation? OD at 260 units is equal to 50 microgram per ml. So if you are getting OD of 1 at 260 nanometers, then it is assigned as 50 microgram of DNA is present per ml. All right. So with this, 1 nanogram per microliter also will be equal to 1 microgram per ml, right? Ratio wise. And so you are going to measure the absorbance at that particular wavelength, that is 260 nanometers, and microgram per ml quantity of DNA will be having one OD of 1. So dsDNA if you have, then 50 microgram per ml of DNA will be having absorbance of 1. If it is single stranded DNA, then 33 microgram per ml will give you absorbance of 1. And if it is single stranded RNA, then absorbance 1 will be observed at concentration of 40 microgram per ml of RNA. So here is another concept that you are getting hypochromic shift, right? Hypochroma, hypo is low, all right? Chromic, chroma is to color. So this change in the OD is referred as hypochromic shift. right? So when you are boiling the DNA, the temperature changes, right? So this is what hyperchromic shift. So hypochromic and hyperchromic. So hyperchromic is absorbance is increasing. So when DNA melts, absorbance increases. It is called as hypochromic shift. So this is another um, what we say application with respect to spectrophotometer, that is quantity when it is very less, that also can be analyzed. Nanodrop technique. Of course, I'm not going to go in much of the details about nanodrop. Now, yes, food, beverages, and any pharmaceutical molecules, all these can be analyzed when you are talking about spectrophotometer. So, presence of any um, contaminating molecule can be detected simultaneously. Presence of the desired molecule also can be detected. Now, when it comes to as the example of oils, so rancidity due to degradation of fatty acids, oxidation of fatty acids will give you rancidity, right? So presence of dienes and trienes of unsaturated fatty acids, which absorb light in the range of 230 to 70 nanometers, can be estimated. And of course, rancidity is going to give you variation in the standard lambda peaks or lambda max values, and you will get to know about the quality of the of the oil, that is desired fatty acid what was present earlier, have it undergone oxidation, because oxidation also is a different form of the same analyte, yet it is not same as the original analyte, right? There is oxidation, so addition of oxygen we are talking about, or reduction when you talk about addition of hydrogen. In terms of electrons also you can define it, but yes, there is structural change. A single atom addition or removal, functional group addition or removal, also can give you variation in lambda max values, and you can comment on the qualities or purity, presence or absence of that analyte under study. Similarly, colorimetric estimation of phosphate is one of the one of the applications. So this is one example. Yesterday we had taken example of KMNO4, CuSO4, etc. So today it is about phosphate. So it is one of the example which is commonly known to you. So here maybe with the chromophores, like for estimation of sugar you use DANSA reagent, DNSA, dinitro acid reagent, or for protein estimation we use biurate or Folin-Lowry reagents, and you get the colors, right? So similarly for metals and other elemental forms, electrolytes, you can use spectrophotometric method for analysis, right? So with this I think we have done with overview of UV visible spectrophotometry. I won't say we have learned it in details, because the techniques that we have to learn is just an introduction of the technique. It is not in depth, because when you say in depth, you have to start with the details of the spectra, then the atomic levels, the energy levels of the analyte, their molecular rearrangements, and what exactly happens with its spectral and energy absorbance, that is light absorbance, how it changes. Example to example also we can go. It's really a very special subject, as spectroscopy itself is a subject. We are learning it as analytical instrument, but spectroscopy in itself is a subject and has lot many applications and different types, and different types of spectroscopy are known, different types of spectroscopic instruments are known, their functions are different based on the IR, the lamp source or the light source that is used, and the functionality of the entire system, but basic components are same. So if you have any query you may ask me right now, or else I'll conclude this session, and again we will rejoin in 5 minutes with FTIR, that is another instrument that we have to talk today about. Is there any difficulty?
No, ma'am.
So please text if you have any difficulty. We have talked about the design of UV visible spectrophotometer in detail. We have to just talk about detectors, which I am going to talk in the end of all the spectroscopic instruments, after we finish talking about different types of spectrophotometers, UV visible, then IR, etc. And after that, we will go to the different types of detectors that are required for analyzing the signals generated by the instrument. So you have FID detectors, you have thermal detectors, you have photo multipliers in that, right? So all these things we have to learn, but it will be a separate lecture on detectors.